Okay, so the second part is for the analyzing questions. These are the last couple pages. So a lot of emails on number 1. People keep asking me what I mean by this. So when I say to draw a model, what I'm talking about here is something kind of similar to the beginning of the school year when we did classification of matter, and you guys had those pictures, and you had some triangles and circles and squares, and some of them were connected to each other and things like that, right? That's a model. That's a particulate model. And we've been drawing those kind of throughout the year, different times, especially in our notes and stuff. So that's all that I was looking for on this one. So when it says draw a model of a dilute solution, basically what you should be thinking is that these particles are going to be a little more spread out and there's not going to be as many, right? Because the whole idea of this lab was that we kept this the same. We changed our molarity, which in turn affected how many moles we had of the solute, right? And so that's all that you're showing here. And so another thing I'd like to point out is that most of our stuff in this lab were ionic solids. So for example, the sodium chloride, it would not exist like that, right? So this would be the chlorine ion and this would be our sodium ion, the positive and the negative, right? And so they're not going to exist together in solution. When they're getting solution, you guys saw a video last week about how when you dissolve things, they split into their different ions if they're ionic. So just like that, we would actually have our chlorine ions and then we would have our little sodium ions separated, okay? And so that's all that I'm going to show in my little model. And you're more than welcome to do this too. And for this section, I kind of put it on the post that you can either hand draw it and then send me a picture of it. You can handwrite this whole thing and send me pictures of it, or you can type it in and use the little Google Drawing app part and stuff like that. So it's totally up to you. So going back to this question, for the diluted one, I would say, okay, there's my water line, and then there's a couple or 3 chlorines, and here are my 3 little sodiums. I'll even color in the sodiums like that. Okay, and so I have sodium chloride, right, that I'm representing in my picture. And so there we have 3 of each, meaning that we had 3 of those ionic compounds in there. And then they all split into their different ions. All right, a concentrated version of this, we would just increase the number of solute moles or pictures that we have in this same amount, this volume. And so let's just go ahead and say, okay, so now I have 5 chlorines, and now I have 5 little sodiums. Okay, that would be a concentrated version. Okay, so a little bit closer together, less solute in the same amount of liquid. And that's basically what I was looking for. Okay. All right, number 2. Number 2 says, how does the scale of matter you're working with prevent you from drawing a model that's 100% reflective of the contents in the 2 solutions? Well, we've been dealing with this all year, right? Ions are super tiny, right? So ions are too small to draw accurately, meaning the same exact number that should be in solution. We don't have, I want you to think of the number, the mole, right? Of a mole of particles, 6.02 times 10 to the 23rd. If you had to draw that many ions just to show a mole, think about it, right? So we're not going to be doing that. So this is the awesome thing about a model, is that it just needs to represent it in a scale that shows the same ratio. So this whole idea, 3 to 3, and 5, whatever, we're showing less solute, more solute, and therefore it's showing it accurately. All right, number 3, how can you tell that the 0.5 molar solution you prepared is more concentrated than the 0.1? So talking about the copper sulfate, and you kind of saw in the video, pentahydrate. Sorry, I guess I should add that. But talking about that, we know that the concentrated was a darker blue, okay, than the lighter one. So that's just referring back to the data table that was given to you in a separate document that I kind of showed in the last video. All right, number 4. Number 4 just says, can you tell which of the two NaCl solutions is more concentrated? Can we macroscopically look at this stuff, so at that macroscopic level, and can we look at those two beakers and be able to tell which one is actually more concentrated? No, both are clear. So you would have to run probably another test in order to figure out which one was actually more concentrated. Okay, so there's no way macroscopically to be able to determine that. All right, do you think the masses of the two copper sulfate solutions you prepared are the same or different? So technically, right, technically we prepared the same volume. So the same volume, and we just changed the number of moles in there, right? So technically, looking at how much was added for one versus the other, you gotta consider two things. So I'm not gonna give you an exact answer on this one, and I just would like to kind of see what your thoughts are on it too. But I want you to think of it like, if we were to just look at the volume being completely the same for both of these, and the mass was technically different, then yeah, it's pretty obvious. The higher concentrated one is going to be heavier than the diluted version, right? However, if you think about the process of making this solution, some of that solute takes up some of the volume. It's not the same exact amount of water every single time. We add the water in to get to this final volume of 100 milliliters. And so therefore, could it have been a little different? Or could it have stayed the same? That's what I'd like to see what you guys would say. So I will kind of leave that one up to you. I'm just more looking to see what you guys would say. Number 6, it says develop model. So why does 100 milliliters of a 0.1 solution of sodium chloride require a different amount of solid than 100 milliliters of that? So what is the big difference between this one and this one? Well, if you look back at questions 1 and 9 and compare them to number 10 from the procedures, we see these smaller numbers compared to something like 12 grams that we had to use, right? Or I'm sorry, I said that backwards. So the copper sulfate for the 0.5 molar solution had 12 grams, and then on the sodium chloride, I'd have to go back and look, but it was a lot less, right? And so when we're looking at that, what is that big difference between these two? And it comes down to different molar masses. And so I want you to put that into your own words. How does that affect that, right? Because what the thing that we are keeping the same is same number of moles for these different concentrations, same volume, but these things individually have different molar masses and therefore will show up as a different mass, right? So that's what that question was going for. And then finally, number 7, if you forgot to label the two sodium chloride solutions, what physical process could you use to confirm there was more sodium chloride dissolved in one solution than the other? And so for this one, I want you to think back to the very beginning of the year, our separation of matter lab. So that was the one where you had the iron fillings and the sand and the salt. And I wanted you guys to get them into 3 piles, right? And then we checked to see, hey, were you able to get it accurately? Well, how did you get this part out of the mixture? Think about it, okay? And then think about what would be the process that you could use in order to determine which one was more concentrated. So that's what I want you to use for that question. All right, well, hopefully this all helped. The video number 1 with the procedure part, and then video number 2 is helping with this analyzing part. So the only other thing that I wanted to touch base on real quick is that, was making sure you guys understood that this one exists, right? So this little equation. This one I kind of gave just in notes. I believe the notes looked, let me actually go over to that page. All right, this was actually the notes that you guys got. It was a doc that was shared with you on Wednesday. So you have the molarity calculations. I think I've shown enough of those in this little video to kind of get you through that. But you also have the dilution equation. And so I just wanted to point out that you have basically two sides to this equation, right? We usually say stock solution and diluted solution. So what we want and what we have, kind of thing, right? And so usually what we use this for is I go back to the storage room in my classroom, and I'm like, oh, hey, I have this 15.8 molar of nitric acid. Okay, nitric acid. But I only need, because you guys have never used 15.8 molar. That stuff is nasty, right? You guys in your labs, I usually reduce it all the way down to about a 1 molar solution of this nitric acid. So what would I have to do in order to have enough 1 molar solution of this nitric acid? Usually I would say I have about 500 milliliters. How would I create this? And so what I have to do before I make this solution is that I sit there and I say, okay, well, if I have a 15.8 molar solution, how much do I need to pull from it in order to create, so watch the process carefully, okay? How much do I have to pull in order to create a 1 molar solution and only 500 milliliters. Now, if you notice in all these examples, they leave it in milliliters, but I think it's a good habit to get yourself thinking in liters, because that's what these mean, all right? Technically, units are going to cancel out. They'll be fine, but I think it's always a good habit to just, hey, you got to be thinking in liters. When we get to gas laws, you're going to have to think in liters again, so you might as well get used to converting all your milliliters to liters for now, okay? So what we would do is we would multiply these two, right? So that's pretty easy. We can do that one in our head, 0.500. And we would divide it by that other molarity to figure out that volume that I would need. So then once we solve for that, I would then pull that, I'd put it into another one of those little volumetric flasks, okay? And then I would add water to the fill line to make that 500 milliliters. Okay, and so it's a very similar process, but that's what this equation is used for. The important thing is making sure that you are keeping your information on the correct side of this equation. Okay, so I think that's all that I'm going to share on this little video. I don't want to make it too long because I know people are waiting for it. But if you have any questions, please don't hesitate to ask, okay? And all my people who are, sorry, a little application of this, all my people who are wanting to be nurses or work in the medical field, those little IV bags, when they are trying to bring that solution over to a patient and they have to inject the patient with the stuff from an IV bag, they aren't given IV bags with those concentrations. They actually do this every single time. So especially my kiddos who want to go into the medical field, this is a very important equation that would stay with you all through your career. You would honestly be starting to do it in your head. And they do it more with percentages, but it's the same process. So just a little FYI. Anyway, let me know if you have any questions, and I will talk to you guys again on Monday.